This is the 10th session on inner product spaces. I am going to talk about orthogonal projection. We are given a finite dimensional inner product space V, and if we fix a vector, non-zero vector U, then we saw how to define orthogonal projection of a vector X in V onto the one-dimensional subspace spanned by the vector V. Now we want to generalize this. Suppose W is a vector subspace of V and take a vector X in V. What is meant by orthogonal projection of X onto W? If you had been carefully following my earlier lectures, this should not come as a surprise how to define that. Okay, let us get started and we will see the uses of that today. Okay, so these are not product spaces. The title I will call it as orthogonal projections. So let us assume B is a finite dimensional inner product space over F. F may be R or C. Right? And suppose W is a vector subspace. All right. Or have I started recording? Yeah. Okay. Right. Since the W is a subspace of a finite dimensional space, this is also a finite dimensional space. Therefore, by Gram-Schmidt process, I have W1. I do not know what is this. Okay, I have W1, W2, WK, and orthonormal basis of W. Right? Okay. Now, what we want to define is, I don't understand what is this. Oh, this may be something which I created, huh? Anyway. So, let us define W perp to be the set of vectors X and V so that the X inner product W is 0 for all W in capital W. Okay, I claim this is a vector subspace. 0 belongs to W perp, that's very clear because 0 inner product W is 0. Right? And now suppose X and Y are in W and X plus Y, I want to know whether it is in W. That means start with any W in W, I have to check whether X plus Y inner product W is 0. But this is nothing other than, we know how to do this, X and Y2. But this is 0 because X is in W and Y is in W, therefore these are 0, therefore this is also true. And similarly scalar. If alpha is a scalar and X is in W perp, oh, this is a, I'm sorry, X and Y in W perp. Okay, then for any W in W, okay, let us look at alpha X W, that is alpha in inner product X W. This is 0, therefore this is 0, right? Therefore we have shown, okay, this W perp is a vector subspace. Okay, and we have a name for that. It is called W perp is called orthogonal complement. Complement of W in P. Okay, let us look at a quick example. Suppose my V equal to R3 with a dot product, right? My W equal to, let us say, YZ plane. Therefore, this is span of R of E2 plus R of E3. Right? Right. Now, if I want to start with any vector X, Y, Z in R3, I want to know whether suppose X, Y, Z is perpendicular to W. That means start with any vector here, X, Y, Z, Okay, and any inner product here is u of u1 plus u of v of u2. Okay, u and v are scalars. Okay, not vectors now, they are scalars. Therefore, this is going to be xu. Okay, so let us say, sorry. So in particular, let us look at E1, x, y, z, inner product x, y, z with the E1. But this is x and this has to be 0 means x is 0. Similarly, we conclude y is 0. Therefore, what have we found? This W per is nothing other than set of x, y, z in R3 so that x is 0 and y is 0, where W is R of U2 plus R of U3. I hope I did YZ, therefore it's E2 and E3. Yeah, just I'm not in mode, it looks like that. See, my W is R of E2 plus R of E3. Therefore, if X, Y, Z, okay, when is it perpendicular to E2? This is nothing other than Y, this must be 0. And similarly, that with inner part E3, that will be Z, that must be 0. Therefore, W per is all wrong. So W per is going to be x, y, z in R3. So that, okay, y is 0 and z is 0. So this is essentially x-axis. Right? Right. Now what we want to do? We want to prove something. Now I want to say my V is a direct sum of W and W per. So let us quickly recall what is meant by direct sum. This means if you give me any vector x, I can write it as W plus Z, whereas W is in W and Z is in W per, and this is unique. That means if x equal to W dash plus Z dash with W dash in W, Z dash in W per, then W is W dash and Z is Z dash. Okay, I hope all of you remember this, right? I want to prove that. The first thing I want to prove is the following. Okay, what is that I want to prove first? Right. So I want to prove the following. Yeah, W intersection W per is 0. Why? Because suppose a vector Z is in W intersection W per, then look at the inner product ZZ. I can think of this Z in W and this Z in W per, right? Therefore, this must be 0. That means norm of Z squared is 0. Therefore, Z is 0. Do you understand? So that's the first observation. Second thing, okay, right. Now, I want to define orthogonal projection. Projection of any vector x in V to W. How will I do that? So we defined orthogonal projection PW of x to be, what do? You take we have fixed already orthogonal basis W1, W2, Wk of W. Therefore, you take the W1 component, W2 component, Wk component. So how do I do that? I'm sure all of you know that this is x with W1, and so on. Inner part x with Wk. Notice that this is an element of W. Is that clear? Right. Now what I want to claim is, let us look at the vector x minus Pw of x. I want to say it belongs to W per. Yeah? Right. To check this belong to W per, what do you think I have to do? See, right? So I have to say x minus Pw of x inner product with any arbitrary W must be 0 for all W in W, right? But remember, W is a span of W1 to Wk, right? Therefore, it's enough to show inner product of inner product of x minus pw of x wi is 0 for 1 less than or equal to I less than or equal to k. Right? But that's very easy because let us look at x minus pw of x inner product of wi. That is equal to x minus, this is what? This is inner product of x with wj, j equal to 1 to k, this is j. Yeah, that inner product with wi. Right? Now all of you are very adept in decoding this kind of inner product. This is going to be x inner product wi minus summation comes out. These are all scalars in the first variable, therefore they also come out x wj and j running from 1 to k. And what do I have? I have inner product of wj with wi. Remember here I is fixed, j is allowed to vary. This we know is delta ij. Therefore this is not 0 if and only if j equal to I. If that be the case, this entire sum becomes inner product is wi. And that therefore this is 0. Yeah. So pause. Review. Proceed. So let us recall. What do you think we have achieved? So W is a vector subspace of V and W1 to Wk is orthogonal basis of W. Then we define Pw of x to be summation x with Wj, j equal to 1 to k. This is what we call orthogonal projection of x onto into W. Then if you look at the z, which is x minus, okay, pw of x, then z is in w per. Right? Now notice that this shows that x I can write as pw of x plus z. And where does this fellow? This fellow is in w. Where does this fellow belong to? W per. Just now we proved. Therefore, what do you think I have proved? I have shown that any vector x in V is a combination of two vectors. The first vector is a sum of two vectors. The first is in W and the second thing is in W per. Okay. And we already know W intersection W per is 0. Right. Therefore, what we have proved is V is a sum of W plus W per. And since W intersection W per is 0, this implies V is a direct sum of W, direct sum W per. Yeah. So this is called the orthogonal direct sum. So yes, we have proved the following. Okay, V of finite dimensional product space. W is a vector subspace of V. Then we define W per to be set of all x in V, so that xw inner product is 0 for every w in W. Then V is a direct sum of W and W per. And this is called orthogonal direct sum because each vector of W and is orthogonal to each vector of W per. So this is called orthogonal direct sum. So we already learned direct sum, but this is something special. Now geometry comes. Okay, any vector in W is perpendicular to any vector in W per. Okay, let's go back to the R3 example I saw we gave. You can see that. Yeah. Okay. So this is what we have done today. Right. Now what is the importance of orthogonal? So let us keep a picture. Okay. So let me, I still have not learned how to look at, is there a pen? Okay, it does not seem to give you different colors. I do not know whether I will be able to write this. Okay, this is my W. and suppose I take this as x, then what you have done is you have orthogonally projected to this. This is PW of x. And right, and this is, the picture does not look very nice. Okay, they are orthogonal. Are you following? So yeah. So if you want, think of this as W. This is a vector x. This is PW of x, and this is your z, which is x minus PW of x. Okay, this is what you have done, right? Now what we want to prove is something very interesting. We want to prove the, okay, you start with the vector x, okay, and let us look at PW of x. This norm is less than or equal to norm of x minus any w, for any w in w. That means among all the points, so keep the picture in mind. Okay, this is your w, this is your x, okay, these are various w's. Okay, now look at the distance between x and w1, w2, etc. The one which is closest is going to be this vector, which is PW of x. Do you follow that? Yeah, this is what we want to prove, right? That's very easy to prove. Okay, how do I prove that? The way to prove that is, let us look at. So x minus w, right? Remember what I said? Whenever I have norm in inner product space, what should I use? Norm squared. I should not worry about norm. Okay, this. Now I have to bring in PW of x. So what? How will I do? I will add and subtract PW of x plus PW of x minus w. Is it okay? This is algebra. Now what do I know about this fellow? This is a vector in w. Right? There is a square, sorry. Right? And what do I know about this fellow? And this is a vector in w perp. This we already proved. This is our z, right? Therefore, the w perp. Therefore, I have written this as two things. Okay, v, or let us say u plus v, where u is in w perp and v is in w and squared. And these two vectors are orthogonal. U and v are orthogonal to each other. Therefore, we have Pythagoras theorem. So Pythagoras theorem tells me this is nothing other than norm of x minus PW of x whole squared plus norm of PW of x minus w whole squared. Right? Now what do you get? See? Therefore, the distance between x and w, the distance squared rather, okay, is the distance squared of x with the PW of x plus some non-negative quantity, right? And therefore, this shows that norm of x minus w whole squared is greater than or equal to norm of x minus PW of x, right? And remember, this we had already used many times. If I have given two non-negative numbers a and b, a is less than or equal to b, if only a squared is less than or equal to b squared. Therefore, okay, x minus w whole squared is greater than or equal to this if only x minus w is greater than or equal to x minus PW of x, right? And when does the equality hold? If the equality holds, if these two are equal, that means this must follow to 0. But that means PW of x must be equal to w, right? So please understand. So what have we shown? We have shown that, okay, if I orthogonally project, okay, a vector, maybe I'll do another page. So if I orthogonally project, this is my w. If I orthogonally project this vector x onto w, this is my PW of x. Okay, this is the point which is nearest to x. Among all points of w, this is the point which is nearest. This is the most important thing. Now, even though I wrote like this, x minus PWx is less than or equal to norm of x minus w for every w in w. Okay, but this we can write a square. So this is the basis of, you will see in applied math, this is very important thing, least square. method of least squares. Okay, perhaps I will produce a very simple example and explain the method of least squares in another video, but this is all we have done. Okay, so learn this well. We will make use of this later. So what have you done today? Given a finite vector space and a vector subspace W, we learned what is meant by orthogonal projection. And using that, what did we prove? We said that any finite dimensional plot space is a direct sum of W and its orthogonal complement W pole. Okay, and using that, we also showed if I take a vector x in V and look at PW of x, which is a vector in W, and the distance between x and PWX is less than or equal to distance between x and any other W. Okay, and this is the base of method of least squares. Okay, but don't worry, this much is what you have learned. We will again come back. Stay tuned.